let us take a look at Bode's method of approximating the frequency response. What we are looking for is a method for finding out the modulus which corresponds to the gain and argument which corresponds to the phase shift of kgh j omega, where kgh is the loop transfer function. So, we are interested in the modulus of this and in the argument of the same thing. Now, of course, k being positive, the modulus of this is the same as the modulus of gh j omega. So, we need not worry about k, we can always take the effect of k into consideration later on, and similarly k being positive, the argument of kgh is the same as the argument of gh. Now, we can of course make use of the pole 0 diagram and get some idea about how these two things change with frequency. Frequency response is the name given to the variation of this quantity with frequency omega. That is the gain variation, the ratio of the amplitude of output to amplitude of input for a sinusoidal input signal, and the phase difference or the phase shift from the input to the output as a function of frequency. It is called frequency response because we used it in our Nyquist criterion. It is called a Nyquist plot, or it is also called a polar plot, because the argument, the modulus and the argument are like the polar coordinates of a complex number. So, from the pole 0 diagram, it is possible to get some idea about the variation of gain with frequency and the variation of phase with frequency. So, for that, let us look at the simple situation corresponding to our feedback control system with proportional feedback. So, we have two poles here, one of them, the two are a result of the two time constants, the electrical time constant and the mechanical time constants associated with the motor and the load. So, we have two poles, no 0, and we want to look at gh j omega. Now, as we saw earlier, we can think of writing gh as a ratio of two polynomials. In fact, I am making the assumption that the system is described by a ordinary linear differential equation with constant coefficients of the kind that we saw a long time ago, and because of this gh as a function of s can be written as a ratio of two polynomials. So, in this case then, when there are only two poles, let us say one of the poles is called P1, the other is called P2. So, what will gh as a function of s look like? Well, there are no zeros. So, in the numerator there will be just some constant or a number a, and in the denominator we will have s minus P1 into s minus P2. This will be the polynomial in the denominator because there are two poles P1 and P2, right. Now, if we replace s by j omega, what do we get? We will get gh of j omega equal to a divided by j omega minus P1 into j omega minus P2. Now, as we saw earlier when we discussed the root locus method, if you plot j omega as a point in the complex plane, then it will be a point on the imaginary axis. Here is the imaginary axis, here is the real axis, and all this is the s plane now, because you are using s rather than z for the complex variable. So, here is the point corresponding to the number j omega, here is the point corresponding to the number P1. Then, as we saw in connection with the root locus method, when we derived the two basic principles, this vector that points from the pole to j omega represents the complex number j omega minus P1. So, I am going to write here by this side j omega minus P1. This vector of course is not from the origin, so it is not the complex number j omega minus P1, but it represents the complex number j omega minus P1. Similarly, this vector from here to here represents the complex number j omega minus P2. So, now gh of j omega is a divided by the complex number corresponding to this vector multiplied by the complex number corresponding to this vector. Now, we know that if we have a ratio of two complex numbers, then the modulus of the ratio is the ratio of their moduli. So, because of this, then we will have mod of gh j omega equal to a assuming A is positive, modulus of A is real, mod of j omega minus p1 into mod of j omega minus p2. But given a complex number j omega minus p1, what is its modulus? Modulus is the length of the vector drawn from the origin to the complex number, or because this vector represents that complex number, the length of this vector. Similarly, mod of j omega minus p2 will be the length of this vector. So, we have gh at j omega modulus, that is the gain at any angular frequency omega, equal to A divided by the length of this vector multiplied by the length of this vector, that is the product of these two lengths dividing A, that is the gain. You remember in the root locus method we talked about distances to the poles and distances to the zeros. Here of course there is no zero, there are only distances to the poles. So, the gain equal to A divided by distance of this pole from j omega multiplied by distance of this pole from j omega. Now, what is going to happen as omega varies? So, think of omega very small, therefore, this point is very close to the origin. Then we have these two distances which are nearly equal to p1 and p2 absolute value respectively. So, as omega tends to 0, the gain will tend to the value A divided by absolute value of p1 into absolute value of p2. Remember, p1 and p2 are negative numbers, negative real numbers. So, I have to write down absolute value of p1 and absolute value of p2. So, this we can call, as we have done it already, as the DC gain, that is the gain at very low frequencies. So, the gain at very low frequencies will have some value like this. Now, as omega increases, what is going to happen? As omega increases, of course, A is the same, but the denominator, which corresponds to the lengths of these two vectors, is going to increase. And as omega increases more and more, the lengths will increase more and more. As a result, the gain will become less and less. And we can easily see that as omega tends to infinity, or this point moves up indefinitely, the vectors become indefinitely long, and therefore the gain will approach 0. And therefore, I can write the high frequency gain tends to 0. And of course, this is something we had already seen in the polar plot. There was a DC gain which was non-zero, and the high frequency gain was 0, or as the frequency increased, the gain kept on reducing till in the limit it would be 0, or the limit of the gain would be 0. So, this is as far as the gain is concerned. Now, what about the phase shift? Now, that also is not very difficult to see from the diagram, because once again, if we have a ratio of two complex numbers, the argument of the ratio is the difference of the arguments, argument of the numerator minus the argument of the denominator. If we have a product of complex numbers, the argument of the product is the sum of the arguments of the two terms of the product. Now, what do we have here? We have A divided by a complex number j omega minus p1 and multiplied in the denominator by another complex number j omega minus p2. So, the angle of g h j omega will be the angle of A. If A is positive, then the angle of A is 0 minus the angle of j omega minus p1 added to the angle of j omega minus p2. Now, j omega minus p1 is precisely the complex number represented by this vector. So, what is its angle or argument? It is this angle, and similarly for the other vector, this is the angle. So, the argument or the angle of g h j omega is 0 minus this angle minus this angle. When we have noticed this, we are now ready to look at the behavior as omega varies. When omega is very close to 0, what are the two angles going to be like? They are going to be very small, almost 0 degrees. So, their sum will also be very small, very nearly equal to 0 degrees. Of course, not quite 0, there will be some small positive angles, and therefore, the argument of g h j omega will be a small negative angle when omega is small. The phase shift will be negative, but small. Then, as omega increases, these two angles keep on increasing, but they do not increase indefinitely, because as omega keeps on increasing, the angles always remain less than pi by 2 or 90 degrees each, and they are getting added up because they are multiplying together in the denominator. So, as omega increases and becomes very large, the two angles will be each of them nearly 90 degrees, but less than 90 degrees, therefore, they will add up to an angle which is almost 180, but less than 180, but because of the factors in the denominator, the phase shift will be close to minus 180 degrees for omega large. And from this then we are able immediately to see that the kind of polar plot that I had sketched last time is correct. For DC, of course, there is no phase shift, but for very small frequency there is a phase shift, and therefore the angle is negative. The gain is of course not 0, not infinity, but it is some finite value. At very high frequencies the gain is very nearly 0, so I am near the origin, but the phase shift is not quite minus 180 degrees, it is an angle little less than 180 degrees in absolute value, and therefore this was the nature of the polar plot that I had drawn when we looked at the Nyquist criterion. So, merely by looking at the pole 0 diagram, in this case there are only 2 poles, by looking at the point j omega on the imaginary axis, by thinking of or visualizing these vectors, looking at their lengths and angles, and looking at what j omega involves, terms in the numerator, terms in the denominator, it is possible to get some inkling of how the gain and phase shift are going to vary. Of course, this pole 0 plot had only 2 poles, so the situation was really simple. If we put more poles, we will see that the situation will be a little involved, and therefore something like what Bode devised is useful. Note that I can, if I want, calculate the lengths and the angles exactly. Of course, by exactly one means up to the precision provided by your pocket calculator or by the computer program. We never really get 100% exact results anyway. So, I am not talking about computing the gain or computing the phase shift or for one particular value of omega or another or 10 different values of omega. It is of course useful to calculate the values, because then we can get a more correct idea of what is going to happen, but qualitatively, for qualitative understanding, I do not need to do any calculations. Whatever calculations I do are not really calculations, but I look at the diagram and I look at some background knowledge, I use some background knowledge I have and conclude that in this case the gain will go to 0, the phase shift will go to 180 degrees, but the phase shift will be with a negative sign, and therefore the polar plot will be like this. Let us take the next example, which is the example of our speed control system once again with the integrator added. Now, the pole 0 diagram has one more pole, so it is this pole here, another pole and a third pole. There are still no zeros, and now we want to figure out how the gain and the phase shift vary. So, once again we think of the point j omega, which is on the imaginary axis, the upper half of the imaginary axis, and then we think of the 3 vectors drawn from the 3 poles to this point. Then the gain is equal to whatever is that numerator constant divided by the lengths of these 3 vectors. So, what is going to happen when omega is very small? When omega is very small, this vector that points from the origin to j omega has a very small length. The other 2 vectors, of course, they do not have lengths which are small or going to 0, but the length of this vector as omega approaches 0 is going to become smaller and smaller and in fact approach 0, and that is in the denominator. Therefore, the gain will tend to infinity, or if I want to talk about the DC gain, then I can qualitatively write the DC gain is infinite. Actually, there is no DC gain, because with an integrator, if I apply an input voltage to the integrator which is constant, the integrator output will go on increasing indefinitely. Therefore, in principle the motor speed will go on increasing indefinitely. Of course, nothing of that sort will happen, because the motor is a linear device only within certain limits. So, what we mean is really as omega tends to 0, the gain tends to infinity. The gain will be very large for frequencies which are very small. So, that information we have obtained from the pole 0 diagram. The next piece of information is about the argument or the phase shift, and that again it is not difficult to figure out. Here is j omega. Now, what do I have to do? The argument of g h j omega is argument of A, which is 0 degrees, minus the sum of the 3 angles made by the 3 poles at the point j omega. Now, this time this pole at 0 makes an angle of 90 degrees at this point j omega, and this angle remains constant as omega varies. As this point moves along the imaginary axis, this particular angle stays put at 90 degrees, whereas these two angles, they will start off with small values and then go on increasing to large values. So, this makes a constant contribution of 90 degrees in the denominator. These two make a contribution which varies from 0 degrees to 90 degrees in the denominator, and therefore, what can we say about the angle of GH j omega? As omega tends to 0, the angle will be pi by 2 with a minus sign. Moreover, these two other angles made by these two poles are not quite 0, and therefore, the angle is going to be slightly greater than minus pi by 2, or in the third quadrant. Whereas, as omega tends to infinity, this angle is pi by 2, the other two angles also are pi by 2 each. So, the net phase shift will tend to minus 3 pi by 2, which is also the same as plus pi by 2. All right. So, with these two items of information about the gain and the phase shift, then we are ready to sketch the polar plot. At low frequencies, the gain is very high, but the phase shift is minus 90 degrees minus a small amount. So, it will start off, let us say, somewhere here. For very high frequencies, the gain is very low, so I am very close to the origin, but the phase shift is almost minus 270 degrees, and therefore, the nature of the polar plot or the shape of the polar plot is like what I had drawn earlier. Now, of course, this is only a qualitative diagram. I have not calculated anything. I have only found out or thought about the limits, limit as omega tends to 0, limit as omega tends to infinity. So, for example, unless I do some calculations, I cannot figure out what is this point of intersection of the polar plot with the negative real axis. Remember that we have to worry about the point minus 1 plus j 0 when applying the Nyquist criterion. So, you would like to know where the point minus 1 plus j 0 is. It here, or is this point itself minus 1 plus j 0, or is it in here? So, the intersection of the polar plot with the negative real axis is something we have to find out. Now, for this point, the phase is 180 degrees, or the argument is 180 degrees. So, in other words, you have to find out the angular frequency omega for which the phase shift or the angle of GH omega is 180 degrees. Now, that is a numerical computation which one can do, and of course, in practice one does choose different values of omega and gets the value of omega close enough to the value where the phase shift will be exactly 180 degrees. Knowing that value of omega, then we can calculate the gain by maybe calculating the lengths of the various vectors, or by evaluating GH j omega as a complex number by doing complex arithmetic on the calculator or with a program. It does not matter what you do. So, qualitatively this is okay, but we may need this information, and for that we will have to do some calculation. So, it is not that no calculations are required at all, but qualitatively we know what is going to happen. Now, this was with 3 poles, but what if the transfer function has poles as well as zeros, and not just 2 or 3, but more? So, let us go back to an example which I had taken in connection with the root locus plot. So, there was a 0 at 2, there was a pole at minus 1, a 0 at minus 2, and then 2 more poles at minus 3 and minus 4. So, we had 3 poles and 2 zeros. Suppose the loop transfer function was like this. Now, what will be the variation of GH j omega as omega varies? Once again, qualitatively, as far as the two limits are concerned, omega tending to 0 and omega tending to infinity, it is possible to work out what the limits will be. Why? Because look at this point j omega here. All I have to do is think of omega very small. So, I am somewhere here. So, what is the gain? Now, the gain is the coefficient that is in the numerator multiplied by the lengths of the vectors from the zeros, or the distances of this point to the zeros, divided by the distances of the point from the poles. So, the whole thing will be some number. What it is, of course, we can even calculate For example, here when this point is very close to the origin, distance to the two zeros is 2 and 2, and distances to the three poles are 1 and 3 and 4, and whatever is the multiplying coefficient k, then this is going to be the gain. So, the DC gain can be calculated quite easily. Omega tending to 0, this will be the limit of the gain. What about the limit as omega tends to infinity? As omega tends to infinity, there are two distances to the zeros which are becoming large, but there are three distances to the poles which are also becoming large, and all the distances will very nearly be equal to omega itself. J omega is this point, so the length of this line is omega. So, as I go moving up, that length will essentially be the length of the vectors. Therefore, I will have k multiplied by omega into omega divided by omega into omega into omega, or this is nearly k divided by omega, and as omega tends to infinity, this goes to 0. So, the high frequency gain will approach 0. So, qualitatively then we know that the low frequency gain will have some finite value which can in fact be calculated, and the high frequency gain will be 0. This much for the gain. What about the phase shift? Well, look at the vectors drawn from the zeros and the poles to this point j omega. Therefore, there are these various vectors, and look at the angles made by them with the positive real axis. Add the angles made by the zeros, from that subtract the sum of the angles made by the poles, and see what the result is going to be. Now, here again the limiting values are not difficult to calculate. Suppose omega is very close to the origin, then what are these angles? What is the angle made by this 0 placed at 2 at this point near the origin on the j omega axis? It is almost 180 degrees or pi, actually a little less than pi, but almost. What are the other angles? The other angle made by the 0 is almost 0. The angles made by the three poles are also 0. So, as a result, the phase shift or the angle of g h j omega as omega tends to 0 will be very close to pi or 180 degrees. So, as the frequency goes down or as we approach the DC end, the phase shift will be almost 180 degrees or pi radians. Of course, will it be a little more than 180 degrees or a little less than 180 degrees? We cannot immediately say. One will have to do a little bit of calculation or estimation to find out what is going to happen, but the limit is going to be this. At that end, the gain was not infinite, the gain was not 0, the gain was some finite number. So, the gain is finite and the phase shift was 180 degrees at the DC end. What about the high frequency end? At the high frequency end, all these vectors will make angles which are nearly equal to pi by 2 each. Of course, the angle made by this 0 is not pi by 2, it is actually more than pi by 2. The angles made by the others are all less than pi by 2, but in the limit they are all very close to pi by 2. So, what is the net angle or the phase shift? From this 0 and from this 0 pi by 2 each, so 2 times pi by 2. From these three poles pi by 2 each, so 3 times pi by 2. So, subtract 3 times pi by 2 from 2 times pi by 2. So, that gives us minus pi by 2 or minus 90 degrees. That will be the phase shift at high frequencies. Of course, whether it will be slightly more or slightly less than this we cannot right away say without making some more estimates or some more calculations. But we know qualitatively that in the limit this is what is going to happen. As a result, now I can sketch the polar plot. What information do I have? Low frequency gain is non-zero, low frequency phase shift is nearly 180 degrees, high frequency gain is 0, high frequency phase shift is minus 90 degrees. So, what will the polar plot look like? At low frequency, the gain is not 0, but the phase shift is 180 degrees. So, I am somewhere here on near the negative real axis. I do not know whether I will be here or here, somewhere there. For high frequencies, the gain is 0, so I am very close to the origin, but the phase shift is minus 90 degrees. Again, I do not know whether I will be on this side of the j omega axis or this side of the j omega axis. Now, I have to go from here to here. Now, this is where it is not immediately clear which way the curve will be. If I want to go from here to here, of course I can be very optimistic and just draw a straight line going like that. It's very unlikely that the phase shift is just going to remain almost constant and then do something miraculously and then go like this. It's very unlikely. Maybe it will go like this, maybe it will go like this, maybe it will go like this. All we know are the limiting values. So which one of these is likely to be the correct or close to the exact variation of gain and phase with frequency? This is something which we cannot immediately figure out by only using this approach, that is pole zero diagram, vectors drawn to the j omega point, angles made by those vectors, the lengths of those vectors, etc., etc. This is something which we had already done in connection with the root locus method. There it was used to determine whether a particular point S was on the root locus or not, and if it was on the root locus, what was the value of the gain k corresponding to that point. That is where we used this idea. All right. So it will be useful to have some other and a little better way of finding out the frequency response, and this is exactly what Bode did. So for that, let us write down the transfer function gh of S as some coefficient, I will call it say k prime, which is positive, multiplied by S minus Z1 into S minus Z2 and so on, divided by S minus P1 into S minus P2 and so on. Where there are zeros, Z1, Z2, etc., there are poles P1, P2, etc., this coefficient K0 is just some real number. Now, I want to find out the gain and phase shift. In other words, I want to find out the modulus of GH j omega, and I want to find out the argument of GH j omega. As before, the modulus of this is k prime, modulus of k prime. If k prime is positive, it is just k prime. In the numerator, modulus of j omega minus Z1, modulus of j omega minus Z2 and so on. In the denominator, modulus of j omega minus P1, modulus of j omega minus P2 and so on. In fact, this is what we did earlier. These are then lengths of vectors from zeros to j omega, lengths of vectors from poles to j omega. Take the product of these, divide by the product of these, etc., etc. Now, this is where our engineering way of thinking or approach comes into play. Of course, if I want to calculate, I just multiply out these numbers and divide by these numbers. If I am doing it on a calculator, it is not really difficult at all. Remember, these are complex numbers, so I will have to use the complex mode of arithmetic. If I have a computer program, then I can write a program which will do the product, that is a program which will do complex arithmetic. There is no problem whatsoever. But as I told you, this was done in the 1930s and 40s, when there were no pocket or desk calculators. We had only the slide rule. Of course, you had the commercial calculators, which essentially did addition and multiplication of large numbers involved in financial competitions. But they were mechanical calculators, very clumsy. So the engineer's tool at that time was essentially the slide rule and the logarithmic and the trigonometric tables. So given that background, and this is where the engineering comes in, instead of a product, I would like to use a sum. Now, that is possible. How? How do you convert a product into a sum or a quotient into a difference? The simplest thing is to take logarithm. So, we take the logarithms or take the logarithm of this number rather than work with this number. And therefore, instead of mod gh j omega, which is the ratio of the output amplitude to the input amplitude at the angular frequency omega, we will look at the logarithm of this. Now, once again, it turns out that although in mathematics, in calculus and so on, the base e is more convenient, for practical purposes the base 10 is a good enough base. So, we look at logarithm of this modulus to the base 10. And then it turns out that at that time, people who had already been working in acoustics, in fact, they had thought of this because the volume of sound that the human being can hear, the faintest sound to the loudest sound that you can hear without going mad, that is a very large range. It is called the dynamic range. Therefore, if you look at the pressure variation or if you think of it as amplitude of oscillation, then the range is very large, and therefore acoustic people were already using something like the logarithmic scale, that they were doing log to the base 10. Now it turns out that this number may turn out to be less than 1 for a range of omega values. Therefore, it is good to multiply it by say 10, so that it becomes not a fraction but can have an integer part, and again it turns out that for historical reasons it was multiplied by 20. This 20 has something to do with power as against voltage. So instead of modulus of g h j omega, which is the ratio of amplitudes and which therefore is the gain properly speaking through the loop transfer function, that is the output voltage amplitude or output quantity amplitude divided by the input quantity amplitude, instead of that we take the logarithm of that to the base 10. So remember, the base used here is 10. So I am not writing ln, I am writing log to the base 10 of modulus, and that also is scaled by multiplying it by the number 20. So we have 20 log to the base 10 of mod g h omega, and this is referred to as the dB gain. This is taken as a unit, although there is really nothing like a unit, because a gain is simply a ratio, but this is referred to as dB gain. That is, a number calculated like this is said to be the gain in decibels. In fact, the number log to the base 10 is referred to as a bell, named in honor of the physicist scientist Bell, Alexander Graham Bell, and then of course if you scale it 10 times it is a decibel, but because of this power and voltage quantities we multiply by 20 rather than by 10, and therefore 20 log to the base 10 of the modulus or the gain, ordinary gain, will be called the DC gain. We can very quickly look at some numbers. For example, if the modulus is 1, then what is dB gain? Log of this is 0, so the dB gain is 0. Now do not think of this as there is no gain in the sense output amplitude is 0. In fact, contrary to it, the output amplitude is equal to the input amplitude. Therefore, there is no gain in amplitude, the amplitude remains unchanged. Decibel gain is 0. What if the output amplitude is double the input amplitude? So the modulus is 2. Then what is 20 log to the base 10 of 2? Well, approximately, and as engineers we do not really care all the time about so many places of decimals, this will be equal to 6 dBs. So a doubling of the amplitude corresponds to a dB gain of 6 or a 6 dB gain. What if the amplitude becomes 1/2? Then there will not be a gain, so it will really be, should be called attenuation, but the gain will be minus 6 dB or the attenuation will be 6 dB, or halving, making something 1/2 is attenuating by 6 dB, or there is a gain loss, there is a loss of 6 dB, or the gain is minus 6 dB. Now as far as the gain is concerned, we do use this engineering approach of converting the product into a sum or a difference by taking logarithms. As far as the phase is concerned or the argument is concerned, fortunately we do not have to be engineers, because the angle of a product is already the sum of angles, or the angle of a quotient of two complex numbers is the difference of two angles. So there is nothing like log required there, and therefore we do not have to really do anything more than what anybody else would have done. But remember, as far as the gain is concerned, the gain that one talks about is therefore not the ratio of output amplitude to input amplitude, but the decibel version of it, that is 20 log to the base 10 of the ratio of the output amplitude to the input amplitude, or 20 log to the base 10 of what one would normally call gain. All right then. So what does this mean? This means that the gain, the dB gain, that is corresponding to g h j omega, that is the dB gain in which we are interested, is given by a sum of dB gains of k prime, or the modulus of that, plus the dB gains corresponding to these factors in the numerator, namely the 0 factors, minus the dB gains corresponding to the denominator factors. Okay. So now let us look at one of the numerator factors, let us say j omega minus z1. Now, this is where we will have to consider several cases. So, the first case will be that Z1 is real, that is the 0 is a real number. Not only that, I will assume that the 0 is in the left half plane, that is, if I were to draw the pole 0 diagram again, the 0 will be somewhere here or here or here. If the 0 was here, then Z1 will be real but positive, and of course, if the 0 was out in the complex plane somewhere, then Z1 is no longer real. So, we first consider the case when Z1 is real and less than 0. In that case, what about the modulus of this? Remember now, Z1 is simply a real number. Although I am writing Z1, it is a real number. So, what is the modulus of this? Well, this is real. So, this is the real part with a minus sign, this is imaginary. So, omega is the imaginary part. So, the modulus is going to be square root of omega square plus Z1 square, square root of the sum of the squares of the real part and the imaginary part. So, it is going to be square root of omega square plus Z1 square. Now, this is the actual gain or the contribution to the gain of this 0, but remember, I have to take log to the base 10 of this and multiply it by 20. Now, if I take log to the base 10 of this, what am I going to get? Log to the base 10 of this, because there is a square root, is going to be 1/2 of log to the base 10 of omega square plus Z1 square, right. Now, this is going to be multiplied by 20. So, the net result is that the dB gain corresponding to a factor like j omega minus Z1 with Z1 real, and I have said less than 0, but it does not really make a difference if Z1 is greater than 0. Why? Because I am squaring it anyway. So, the dB gain is given by 10 log to the base 10 of omega square plus Z1 square. So, this is the exact expression for the dB gain corresponding to that factor j omega minus Z1. Now, of course, if you were in a calculating mode, you can change or take different values of omega and calculate these numbers. But as I said, Bode's intention was not to do any detailed calculations, but to get some qualitative information. So, as before, we look at the two extreme conditions, but we will look at something else. So, as omega tends to 0, the low frequency end or the DC end, what is this going to look like? Omega square is very small, Z1 square is what will remain. I am assuming that Z1 is not 0. So, Z1 square is a positive number, omega square however is going to 0. So, this whole thing will approach 10 log to the base 10 of Z1 square, or therefore, it will be this square. So, 20 log to the base 10 of Z1. So, if I know the location of the 0, then 20 log to the base 10 of Z1 will give me the DC gain. So, corresponding to this factor, there will be a DC gain of this amount, 20 log to the base 10 of Z1. So, that is the behavior as omega tends to 0. Now, the behavior as omega increases without limit, or as we say omega tends to infinity. In that case, what about 10 log to the base 10 of omega square plus Z1 square? Now, Z1 is of course fixed, it is omega which is now increasing. So, this becomes negligible compared with omega square for a large omega. Therefore, this whole thing comes down to 20 log to the base 10 of omega. So, as omega changes, the gain changes, and of course, it changes logarithmically because the gain is dB gain and not the original gain. No wonder, do not get worried by this log 10, we have already taken log, that is why there is log 10. Otherwise, the gain will be simply proportional to omega as we saw earlier. So, it is as a function of omega, it looks like log to the base 10 of omega. Now, here is where one more engineering example of engineering aptitude or approach comes in. If something is a function of log 10 of omega rather than omega directly, of course, I can say I can always calculate log 10 of omega, I need a calculator or a log table. But why do not I consider log 10 of omega as the independent variable? That is, instead of frequency omega as say so many radians per second corresponding to some practical frequency in hertz, why do not I think of log to the base 10 of omega as my independent variable? That is, instead of omega varying, I am varying log to the base 10 of omega. This was the idea that Bode used. So, for a moment, suppose instead of log to the base 10 of omega, I think of this as a variable, let us call it say u. Then if u is my independent variable, the dB gain is nearly equal to 20u as u tends to infinity. Geometrically, this is very easy to interpret, because if a function is given by 20u, then what is its graph going to look like? This as a function of u. It is going to be a straight line passing through the origin with a slope of 20, right? This is exactly what Bode did. Now, when you plot log to the base 10 of omega rather than omega, this is said to be plotting omega on a logarithmic scale. This is something which you may have studied, but it does not matter if you have not studied it. We will look at what it means. What it means is that I am going to show log to the base 10 of omega on an ordinary, therefore linear or uniform scale. So, suppose I have this scale here, I have a straight line here, which is my u axis now, and I am going to call it log to the base 10 of omega axis. Then let us say what are the various values of u that are possible. Now, the first thing that you realize is that u cannot be 0. Why? Because u is the logarithm. So, what are the values that are possible? So, with omega equal to 1, what is the value of u? U equal to 0. So, let us say here is the point u equal to 0. With some other value of omega, I will get some other value of u. Let us take omega equal to 10, and we see why, because log 10 of omega is 1, so u equal to 1. So, here is the point u equal to 1. Let us take omega equal to 100, that corresponds to log to the base 10 of 100, which is u equal to 2. Now, I am going to draw or use a uniform scale on the u axis. So, this will be u equal to 2. Of course, u equal to 0 corresponds to a frequency of 1 rad per second, u equal to 1 corresponds to a frequency of 10, and u equal to 2 corresponds to a frequency of 100 or 10 raised to 2 rad per second. Now, you can imagine that instead of thinking of frequency in rad per second omega, we can think of f, which is in hertz or cycles per second. However, this is a uniform scale. So, what about the point u equal to minus 1? What will be the angular frequency to which it will correspond? What will be omega such that log to the base 10 of omega is minus 1? Well, it will be 0.1 or 10 raised to minus 1 rad per second, and similarly u equal to minus 2 will correspond to a still lower frequency of 0.01 rad per second or 10 raised to minus 2 rad per second. So, we have these various values of omega, the corresponding values of u, but omega equal to 0 cannot be shown here, because strictly speaking, if I do calculate or take the limit of log to the base 10 of omega as omega tends to 0, I will get what? Minus infinity. So, that point will be way out here towards the left. So, I am not going to be able to show it. Now, this interval, say from u equal to 0 to 1, there is a change in value of u by 1. What about the change in the value of omega? It is from 1 to 10, that is, it is by a factor of 10. Now, instead of saying factor of 10, one uses a term from music or acoustics, which is called a decade. In fact, the acoustic term is not really decade, the acoustic term is an octave. What we have here is a decade. U equal to 0, u equal to 1, omega equal to 1, omega 10 times that, u equal to 1 to u equal to 2. The interval here, as far as u is concerned, is 1, but the frequency range is from 10 to 100. So, here the frequency range was from 1 to 100, a difference of only 9 radians per second, whereas here it is from 10 to 100, a difference of 90 radians per second. So, that is why one refers to what we have drawn as a logarithmic scale for omega, although it is a linear scale for log to the base 10 of omega. And this, all this is being done because in the magnitude expression or in the gain expression, we have log to the base 10 of omega, and we sort of disguise it by calling it u, so that we get a linear function like 20u. Fortunately, one can go to the market and buy a paper in which the horizontal axis is not only calibrated with a uniform scale, so to speak, from one point to another, which covers a range of a decade, but with points marked in between in a very special way. And such a paper is known as what we need is a paper known as a semi-logarithmic paper. So, a semi-logarithmic graph paper is what one can use in this connection. Now, what is this nature of this graph paper? Let us look at this interval from u equal to 0 to u equal to 1, and let us look at some intermediate values of u. So, here is u equal to 0, here is u equal to 1. So, these are the values of u. The values of omega are of course 1 and 10. Remember, u is equal to log to the base 10 of omega, right. Now, let us take some intermediate values of omega. Let us take omega equal to 2 rad per second. What will be the value of u? Log to the base 10 of omega is approximately 0.3. I hope you have not forgotten the logarithms of some of these simple small integers. So, log to the base 10 of omega is 0.3, therefore, the corresponding value of omega will be 0.3. Now, u equal to 0 here, u equal to 1 here. So, where will the point u equal to 0.3? It will be somewhere here, about 1/3 the distance. So, this corresponds to a frequency of 2 rad per second. So, here is 1 rad per second, here is 2 rad per second. What about another point? Let us say omega equal to 3. What is log to the base 10 of 3? It is 0.4771. So, the point corresponding to it will be almost halfway. So, this will be 3. What about 4? 4 of course is square of 2. So, the log to the base 10 of 4 is nearly 0.6, and so the point will be here. So, this will correspond to 4. What about 8? 8 is the cube of 2. So, it will correspond to u equal to 0.9. So, I will be very close to the 1 point here. So, here will be 9. So, if I now draw the ordinates through these points. So, here is the ordinate corresponding to 1, here is the ordinate corresponding to 2, 3, 4, 8, and this is the ordinate corresponding to 10. So, these ordinates get closer and closer to each other as we proceed from the lower end of the decade, say 1, to the higher end of the decade, say 10. So, if you look at this semi-logarithmic paper, the vertical lines, if you hold the paper properly, will not be equally spaced, unlike an ordinary gridded graph paper, but it will have non-uniform markings of this kind. Of course, no numbers will be written there. So, you have to look at it and then interpret it appropriately, that starting at one point you have a decade, then the successive markings are 2, 3, 4, of course 5 is 0.6991, so it is somewhere here, and 6 and 7 and 8 and 9 and so on. So, the ordinates get sort of crowded together as you proceed from one end of the decade to the other end of the decade. In fact, this is something you have to learn the first time you use the semi-log paper. You can use it upside down. So, you can do it this way, and then this will correspond to 1 and this will correspond to 10, but then these markings are not correct. This is a mistake which students very often do. So, first of all, you must hold the semi-logarithmic paper properly and then use this semi-logarithmic axis for writing down the values of omega. And the typical way of doing it is to start with a frequency which is a frequency like 1 or 10 or 0.1, and then go to the next decade and mark it down as say 10, then the next decade mark it down as 100, the previous decade mark it as 0.1 and so on. So, in other words, what you may end up doing then, depending on the frequency range of interest, will be something like this. So, let us say here is my 1, here is 10, here is 100 and here is 0.1. So, I have used 3 decades or 3 cycles. Then there will be this ordinate here, there will be the ordinate here, there will be the ordinate here, and the ordinates here will be in what way? 2 will be nearly 0.3, 20 will be here, 0.2 will be here, then 3 will be closer, 4 will be closer, 5, 6, 7, 8, 9 like that. Similarly 2, 3, 4, 5 like that. Here also 2, 3, 4, 5 like that. So, they get closer and closer as we proceed from one frequency to a frequency which is 1 decade above it, to another which is still 1 decade, and the third one which is one more decade above it. The total range covered is a frequency range from say 0.1 radians per second to 100 radians per second. This is typically the frequency range that one uses in control system practice. You do not really run into kilohertz or megahertz frequencies or corresponding frequencies in radians per second. So, this is the semi-logarithmic paper. So, get for yourself a semi-logarithmic paper, and we will do some plotting on the semi-logarithmic paper when we look at Bode plots.